Spectroscopy continued. We expect vibrational rotation to occur at the same time. However, when molecules are irradiated with infrared radiation, what is observed depends more on the resolution of the instrument used. Here's an example. This is the kind of band you will get when you irradiate a given molecule with infrared. It's what we call the band envelope. This is normally obtained at low resolution. Let us push the resolution up a bit. Okay. Now, when we do that, we obtain two of them now, that band and that band. Now, this band belongs or is due to delta J being -1, and the right is delta J being +1. The right-hand side one is called the R band, and the left-hand side one is called the P band. Now, this is a shape very characteristic of the atomic molecules. Let's push the resolution a bit even further. We obtain lines under the envelope. These are due to the rotational transitions and are shown in the diagram below. As you can see, this was our P and that is our R branch. And we said the P branch was due to delta J is equal to -1, which is emission, while delta J is equal to +1, which is absorption. Now, as can be seen, inside these big bands, there are lines due to rotational transitions, as shown here, as shown in both envelopes. Now, if we represent this on energy diagrams and the peaks, this is what we obtain. Right? Now, this is the band where V is equal to 0, the vibrational level V equals 0, and that is where V is equal to 1. Now, the transitions are shown in red arrows, with, of course, the first transition here, J double prime being equal to 0, and in the next one, J prime is equal to 0, 1, 2, 3, 4, up to 6. The transitions are between, for instance, that and that. That is 1, or call it 2 to 0, 3 to 2, hence satisfying the -1. Whereas on the other side, we have 2 to 3, satisfying the delta J is +1. And those peaks can be represented in terms of intensity and positions as shown here. Of course, on the right we had the R, so we have R0, R1, R2, R3, R4, R5, and on the other side we have the P1, P2, up to P6. Now, the separation between the two peaks in the center is 4B, because from there to the center is 2B, and from there to the P first peak is 2B, so that makes 4B. Otherwise, just as before, the separation between the lines both on the left, on the P side, is 2B, and also between the peaks on the right side is also 2B. Here is a picture or a photograph of the real peaks as shown. First, in a smaller way here, they are expanded so that you can look at what's happening there. We will discuss these ones later. As you can see, they are at a much, much higher frequency. Again, same thing here, shown more clearly. For the R branch, delta J is equal to +1. Delta EVR is equal to H nu naught plus 2b into j plus 1. For the p branch, delta j is equal to minus 1. Delta EVR is equal to h nu naught minus 2bj. The spacing of these lines, as mentioned earlier, is to be still, meaning that the spectrum we obtain is similar to the pure rotational spectrum, except that here we also observe lines due to transitions due to delta j is equal to minus 1 as well. This type of spectrum is only obtained when molecules are independent of each other as molecules as much as possible. This is almost achieved in the gaseous state. The above picture holds for diatomic molecules and for those which do not have any absorption in the middle at nu equals naught. But for non